All right, welcome back. We are GAME3001 in the summer 2020 semester, and it is week 11. And during our lecture broadcast, we're going to be talking about goal-oriented behavior. So this is part 1. Part 2, we're going to host around from 3 to 5 today, which is going to be our lab. Again, in the lab, my plan was to go over your assignment number 3 with you. And kind of talk about any issues. I'd like to try and give you some feedback about some of the stuff that I've already seen and look at your materials. So I think it's the lab is going to be important. There might not be a lab exercise today, but what I was hoping to do is go over some code and talk about some, your actual your assignment number 2. And then, assignment number 3, and take a look at, what you guys have submitted, any submission issues. I want to look at all that kind of stuff today, because at the end of the day, it's going to be the basis, the foundation for your assignment number 4, right? Which is, again, I want to remind you from a kind of a schedule perspective where we sit, which is an important thing. Because right now, we're sitting at week 11, and if we look at our schedule, which is on Blackboard, so if I go to course information on Blackboard, and if we look at our schedule, this is something that's been shared with you, right? Then you can see we're sitting at here, goal-oriented behavior, and we're going to start talking about utility AI a little bit, what that is, and then we're going to get into some special topics next week, which is our last week really of lectures, right? So because we're sitting at, again, we last week we talked state machines, right? This week we're talking goal-oriented behavior and utility AI, what that is. And then next week we're going to get into a little bit of a special topic, which is machine learning for games and reinforcement learning. How does that work? How do AIs learn, and what's the future? Are they doing it? In games today, are they? How's that working out? So that is really our strategy for for what we're going to be talking about over the next 2 weeks. And again, remember that assignment 4 will be due at the same week as your final exam, and your final exam will be based on everything from the second half of semester up into and including the machine learning for games section. So it'll be including all this stuff, right? So decision making, behavior trees, state machines. It will be true, false, multiple choice. It'll be an online test. You'll get 2 attempts, all that kind of stuff, and it'll be in 2 short weeks, right? So it's not so far away, at the end of our time together, right? So it's coming up, and it's quickly approaching, right? In terms of how fast things are going to resolve, right? So that's I wanted to bring it up to you to make you understand that time is short. We're sitting at week 11, and in a couple of weeks your assignment 4 is due, and then your final test is going to be out there as well. So just letting you know. So that is our schedule. Any questions around that? Around anything like that? Because I think these are good things. These are good, kind of stuff. So designing game AI, we were going to do that as well. We've removed this piece, designing game AI, from our because we've incorporated some of this, the design of AI, in our program. But what I want to talk about is utility theory. It says week 13, but I'm going to talk about it a little bit today as well. So that's going to be the second part of our lecture. I will post the slides for this one as well. So even though it says week 13, it's not really week 13. Remember that this is a kind of a schizophrenic semester in some ways, right? So we're going to start with goal-oriented behavior, and we skip over to utility theory, which is kind of, there's relationships between the two. Okay, so that's kind of stuff that we're going to be doing today. And like I said, I'll post the lecture notes on utility theory and all that kind of stuff very, very shortly, right? So any questions at all on what we're doing today? let's continue. So we'll start off with goal-oriented behavior. So up until now, really, we've talked about decisions, how to make decisions, but yet we need to have, sometimes AI will have some kind of goals. For example, there might be a hunter type of character, or an autonomous character could have some kind of desire to live or collect resources. And games that are simulations, like for example, like The Sims and other games like that, can really show off, the idea of goal-oriented behavior, right? Where they have a goal and it affects their decision making, right? That's different than just making decisions, right? It's almost like, what is the underlying reason for this AI to exist in the first place, right? Kind of thing, right? So where it really comes into, makes sense to use is for people simulation games. For example, things like, the people would eat when they're hungry, sleep when they're tired, and all that kind of stuff. That is where we see it a lot. And what kind of technology would we use from a goal perspective? Would we use a decision tree? As an example, how do we do it? So maybe decision tree is not so good as a solution for goal-oriented behavior. But one of the things we want to kind of talk about is this idea of the AI having one or more goals called motives, right? So motives is the key word here. Again, the AI could have a lot of different goals. A lot of times, the motive for the AI, for example, could be something like, if you're a guard, what is your motive? It's to patrol. You want to make sure that the area is secure. Right, and if you spot an enemy, either you're going to defend or you're going to hunt and kill. Right, one of the those kind of things. Right, and then maybe you might have sub goals like staying alive. Right, the guards are, if they're more realistic and they're not just guards that are come at you relentlessly with unlimited morale. And we've seen games like that where the guards just keep coming at you and they don't care about their own personal safety. Right. Especially older games with AI, it's more like you have an enemy, and the enemy's coming at you, and you're basically gonna attack it. If you don't, they're not gonna run away when they get hit. They won't even try to heal themselves. They'll just keep coming at you until they die, right? And that makes it for, again, a less realistic experience than if you have several goals, especially things like okay, I want to regenerate health, or I want to do whatever. One thing that we have, we have goals that are called motives from an AI perspective, and each goal has a level of importance called insistence. These are just keywords that we're going to use. Again, high insistence will influence the AI strategy stronger than a lower insistence. So that's kind of something we have to keep in mind. So when we talk about these things. And now whenever we think about these business rules, we're talking about business rules. I say business rules for the application we're running. And we're making an AI application and we want to write these business rules. How do we translate these business rules? I have motive and insistence. How do I translate this stuff into code? And that's always the challenge for me anyway. So one thing is the goal, the AI will try and fulfill the goal and reduce its insistence. So what that means is it's going to swing from I have a high insistence, I need to eat, right? And I want to try and reduce that number lower and lower, as an example, until it's very low. But some goals, like it says here, can't be completely eliminated. For example, it's going to come back. I'm going to feel hungry again, or I'm going to lose health, or whatever. I'm going to need to refuel, as an example. Something, right? That's going to increase insistence. And if you have these goals in the background, so for example, if my need to eat goes up higher and higher and higher as I'm patrolling as a guard, right, then that means that after a certain amount of time, I'm going to have to go back to the guard station and switch, right, with somebody else, which is going to create a potential hole in my defense. But it's also going to make it more realistic that, hey, the guard needs to rest. Maybe he's tired, or he needs to eat, she needs to eat, that kind of thing. So that is going to affect our overall behavior for the AI. And it sounds like funny, it's like we have a guard that needs to eat and it's an AI. But it makes it more realistic again. And the more realistic, the more playable, the more fun it can be, and less predictable. Again, we don't want to make an AI as predictable as the guard is always going to go down here, turn right, and then go here. That's not as nice. Unfortunately, most games still have more of a predictable kind of behavior for a lot of the AI that's baked into the game. So we have actions, right? And actions are going to be basically based on what the motives are and how much insistence there is. So again, think about insistence as a number. I have a level of insistence for a particular motive, right? Example, I have a level of insistence for sleep, right? My level of insistence when I first start off in the day is low, right? Because I just woke up. But as as the day goes on, my level of insistence for sleep or rest, whatever you want to call it, goes higher and higher. It ticks up a little bit. And then until, as an example, I need to sleep, right? Or maybe something bad is going to happen. Maybe I'm going to lose endurance, or I'm going to lose strength, or I'm going to have less concentration. I won't be able to have good line of sight. I lose line of sight every so often, or something, right? You can make all these things part of the AI behavior. So again, here's some examples of our goal and how it's linked to actions. So again, I have a goal that's eat, so with an insistence of 4, and my goal is sleep with an insistence of 3. If I take some action, for example, I get raw food, right? Then my goal for eating goes down to 3. My insistence goes down to 3. If I get a snack, my insistence goes down to 2, right? If I sleep in a bed, my insistence, I subtract 4, kind of thing. So these are the things that you can, depending on the actions you take, you can reduce your insistence by a certain amount. This is an approach to this problem, right? So again, I made a problem. I have an insistence I have to take care of, this need for the character, right? And then some kind of action that's going to fill that need for a temporary time, a very small amount of time, right? Why? Because it's going to come back, because everyone has this insistence again and again, right? Even things like collecting resources. I think this is goal-oriented systems are there for resource collection kind of games, where then there's a need to build. I always need to build something, right? In order for me to build, what do I need to do? I need to collect resources, and when I finish collecting resources, then I start to build, and then when I'm done building, I need to collect resources again, right? So it's like you can use it for both ways. So here we have some examples of some goals. And how it works from an action perspective. We have two things, actions and goals. And this is going to come up when we talk about utility in a few minutes. You're going to see how this works, right? And this is why goal-oriented behavior and utility AI kind of work hand in hand. And we'll talk about what utility AI is in a second. So I'm not going to go over too much of this pseudocode, but basically what's going to happen is, depending on what the best utility is, and it talks about utility here, right? It's the action that's going to come out, and we'll talk about that in a bit. Okay, I'm going to skip over some of the pseudocode and go right to this part. There's also something called discontentment. That's another way of thinking about things. So there's two approaches. One approach is with goal-oriented behavior is, okay, I have an insistence, I have a need, I need to fill that need, right? But the other way to think about it is, the higher my needs are, then I have this idea of discontentment, right? So depending on my overall needs, as an example, I might have multiple goals, and each goal has a certain insistence. For example, my need to go to the bathroom, my need to eat, and so on. If I drink soda, then my eating goes down, but my bathroom goes up, right? Because I need to go to the bathroom. The one goal can impact another goal. Then my level of discontentment is my overall insistence level. If I add up all my insistence, as an example, which is, I take all the different goals that I might have as a character, an autonomous character, and I create a discontentment value, if you will. And that discontentment value is going to be the thing that is going to drive me as well to accomplish some of my goals. And I'm going to go with the highest level of insistence, obviously, right? So, for example, if I really have to go to the bathroom first, and it's more important than the other things, and that's going to reduce my discontentment the most, overall discontentment, then that's what I'm going to do first, right, as an example. And you might be able to weight these things, create weightings for these things, not just a value of discontentment, but also maybe some, you can play with the insistence values, so that way certain things don't go down as much. It takes a lot more more actions to bring the discontentment down overall. So here's an example when we add this new value. So we have discontentment. So we have eat 4, bathroom 3, drink soda, eat goes -2, bathroom goes +2. Afterwards, my eating level is 2, my bathroom level is 5, my discontentment somehow is 29, right? As an example, because I have some kind of weighting for my bathroom versus eating scenario. If I visit the bathroom, my bathroom goes down by 4, right, from 5 to 1, let's say, or 5 to 0, and then afterwards, my eating, I need to eat, but my bathroom is 0, but my total discontentment is 16, which is lower than 29, which is a good thing, right? Again, this is based on some kind of weighting for each of the goals, as well as for the insistence of the goals themselves. So it's kind of interesting. So again, these are additional. We can wrap additional values around some of this stuff to create scenarios where we need to take actions for our autonomous characters. Right? That's how it works. So far questions around this, because one idea kind of adds to the other thing. So kind of like we start off, okay, we talked about insistence and we talked about motivations, and now we're talking about discontentment, which is kind of an overall insistence as an example. Okay, I continue. So again, a little bit of pseudocode around this. We choose an action based on, we have actions and goals. We pass actions and goals into a choose action. We create the best action based on the discontentment. We calculate discontentment by taking the array of actions, all the different actions, weight against the goals, and then we have of the best value as an example. And due to the best value, we create for every action in actions. We look at all the different actions, and we want to compare the value of the current action from a discontentment perspective, if we were going to take care of it, compared to all the other actions. And then we want to compare that if this value is less than the best value, then we want to say that we want to kind of swap out. This is kind of a swapping algorithm where we're going to say that the best action is equal to the action with the highest value. That's what this is basically doing for us. And this is going to lead us to, kind of take the next action that's going to reduce our discontentment. Okay, I'm just going to move on. I'm not going to talk too much about that. That is just an idea of how it works. One thing also is another wrinkle that we can add into our AI is the idea of timing. So, for example, we might say that it takes a certain amount of time for you to accomplish that action in game time, as an example, not in real time. For example, maybe my goal to eat changes at +4 every hour. My bathroom changes at +2 every hour. When in order for me to eat, to reduce my motivation and my insistence of the eating insistence, it will drop by -2, but that's going to take 15 minutes, right, as an example. So really, if you think about this in terms of game time, when we start adding these together and using some weights and measures here, afterwards, right, after I eat, which I got, I lowered my eating insistence from 4 to 2, but it took me 15 minutes. Well, if I take 15 minutes and I prorate it over the time, how long it takes per hour, then my bathroom just went up, right? Because it took me 15 minutes to eat, right? My discontentment you know, as an example, is at level 16.25, whatever that means, based on our weightings. If I eat a main meal, that's the next thing. So a snack takes 15 minutes. Eat a main meal takes an hour. Reduces my insistence of eating -4, so it brings me down to 0, yes. But my bathroom now goes up to 5, and my discontentment is higher because I need to go to the bathroom, right? And it's maybe the bathroom, as an example, weighting is higher at this level. So you can see that even though I ate, my discontentment actually went higher from 16.25 to 25. And my goal for my autonomous character is to reduce discontentment. So now, if you notice, if I visit the bathroom, it reduces it by -4, right, as an example. You know, it takes 15 minutes to go to the bathroom, and then maybe my eating is going to go to another level, right? So again, so time is important. So time can actually be something that can affect, you know, another wrinkle, like I said, that can also add realism, especially when you're doing a simulation. I think from a simulation perspective, when we talk about it, we think about you know, creating a simulation for like, not just the Sims, but even for other kinds of AI that we like to create for our first-person shooter kind of games or whatever. The more complex, especially role-playing games, I would say role-playing games and simulations more than shooters, but the more complex your motivations and your discontentment can be, as an example, in terms of wrapping it in with timing, then again, the less predictable your AI is going to be, and the more fun to play. Again, going back to that idea, right? Okay, and so here we have more stuff around pseudocode. I'm not going to go into that. So that's another approach. They talk about something called smelly goal-oriented behavior. So it's almost like, remember we talked about you know, the detection radius for assignment number 4, when the smell leads to a you know, can be kind of lead us towards a goal, like almost like how we also have you know, different kinds of motive sources, right? And that increase or decrease our discontentment. Okay, so a good example of that is we can detect that if we go into a, you know, we have a motive as an example that we want to fulfill, and we have an insistence for that motive, we can detect where a signpost or a waypoint where it can reduce our, you know, our insistence for that particular motive, and that's how it would work for smelly goal-oriented behavior. I'm just going to go into rule-based systems for a second. So we're moving into rule-based systems. Any questions around goal-oriented behavior? So again, for goal-oriented behavior for your midterm test, the things you need to know that we're going to ask you about are things like, so when it comes to goal-oriented behavior, what are the you know, what are the particulars, if you will, right? So one of them is, like we said, motives. Every AI is going to have, in a goal-oriented behavior scenario, is going to have multiple motives, right? Each motive is going to have a level of insistence, things that are going to drive the character to accomplish those motives. Each level of insistence, when you add them up or weigh them, in terms of you know, importance or level of importance, as an example, it will add up to a total discontentment for the AI, right? And satisfying each of the motives by taking actions, right, it's going to take time, and that time, depending on how the insistence grows over time for a particular motive, right, and how long it takes for you to satisfy the motive, can create a more interesting scenario from a simulation or an RPG perspective. Whoa. Okay, that's the summary for goal-oriented behavior. Now we're going to talk about rule-based systems. All right. So this idea that we have, you know, conditions and actions. So we've talked about this before, right? Where we say, well, the captain's health is 51. Johnson's health is 38. Sale's health, or Saleh's health, is 42. Sorry, Whisker's health is 15. These are all, kind of the examples. And the radio is held by Whisker. Well, if Whisker's health is less than 15 and the radio is held by Whisker, then, do something. If Whisker's health is 0 and the radio is held by Whisker, then Saleh pick up the radio. Right. So this is like a rule-based system that we can use, where we have multiple characters or multiple AIs working in tandem with one another in order for them to accomplish a particular goal outside of their regular motives. Okay, so that is how rule-based systems come into play. Here's another one. 15 kilogram fuel remaining, 100 kilometers from the base. Enemy sighted. This is the situation. Enemy 42 and an enemy with 21, and we're currently patrolling. This is the state of a particular of the game right now. Remember we talked about states. These are properties of this state. 15 kilograms of fuel, internal properties. 100 kilometers from the base, all internal, right? Enemy sighted, external, right? And we're internal state is currently patrolling. That's what we're doing. If the number of sighted enemies is greater than 0 and we're currently patrolling, then remove currently patrolling state and add attack first sighted enemy, whichever the enemy is that that we've sighted and the closest one. Okay, so again, another example of a rule-based approach. Now this looks very much like decision trees, all right, but you can see that there are multiple conditions here that can affect the outcome, which is what this is. There's this idea of chaining, where we have forward chaining and backwards chaining. So how forward chaining works when it comes to rule-based systems is it starts with some kind of information, and we repeatedly apply the rules that we've kind of put into place to change the database. Okay, so this is much more commonly used this way. So for example, going back to that previous scenario, right, we have information, right, and once we have this information, we change our actions, and the action changes the database in terms of status, in terms of state. So now we're moving from currently patrolling, which is one state, into an attack from first sighted enemy state, as an example. Okay. So that is forward chaining. Backwards chaining, it goes the other way around. It starts with data that could be considered a goal or motive, right? And then the system works out a series of reactions, if you will, that would lead to the current database, to the goal, right? That's what it works. And then it kind of looks at the then contents, what we do after. So it's kind of a backwards approach to the problem. When it comes to the database, each piece of data, and when we talk about a database, there's different ways to approach this. This could be a JSON file that's stored on a system. This could be a full-fledged database that's on a server somewhere. Typically not, unless it's an online game or something like that. But more or less, that this information that we have in the database is going to drive our rules, our actions. Basically, for example, here are some conditions. The patrol zone, if we have fuel that's 1,500 kilograms and we're inside the patrol zone, then we're going to keep on patrolling, as an example. Okay. Now, I'm not going to go into too much detail here. The rest is more or less pseudocode to support rule-based systems. But really, when it comes to rule arbitration, which one to do first, you always think about the first applicable rule. This is kind of the way that it would work, first applicable rule. You want to look at the least recently used, so it kind of promotes this idea of non-deterministic behavior, right? Sometimes what we might want to use is a random rule, again, to support this. We want to maybe use the most specific conditions, so the more detail from our database, if we can get almost like from a specificity perspective. So we have all these, the goals, as an example, affect or the rules affect the goals, but there's many rules for a specific goal, or if you can almost like kind of dig down deeper and deeper in different levels, then the most specific the conditions are, that's the higher priority. Okay, so there's different ways of creating rule arbitration, because you might have multiple rules that conflict. Which rule is the one that you're going to use over another one? All right, so that is, in a nutshell, goal-oriented behavior and rule-based systems. Okay, and this leads nicely into the next topic of discussion, which is this idea of utility theory. So normally I present these in 2 different weeks because utility theory takes a little bit more thinking. But let's think about what this is. Again, we just talked about motivation. And theatrical actors do this kind of thing too. They say, what's my motivation when they try and act? AI, when we think about this, they use the same kind of idea. They kind of sit there and say, what is the motivation of my character? What is their real need to be there? Again, this applies very well for non-player characters. As an example, it could also appear for minor characters, minions, and that kind of thing. What is their motivations? Okay. So utility theory, really what it does is it gives us a model to calculate the overall utility of an action. Okay, this is what we're talking about. And so we talked about utility very briefly in the pseudocode in the previous PowerPoint. But basically how it works is this. You have a bunch of available decisions, and we want to score each of the decisions with some kind of mathematical formula. And the agent selects some kind of course of action based on the best scoring options, right? So again, look what we've talked about today. Motivation, insistence, discontentment, right? These are values that we can use. And the best action, the best course of action is going to be based on, it's going to be the highest utility, right? So even think about from a decision tree perspective, or a behavior tree perspective. How do I create, how do I compare, as an example, how do I go from one decision to the other when there's more complexity involved? And it's this idea of utility, right? So again, the general concept of utility is that every possible action is scored at once, and only the top scoring actions is chosen. All right, so think about that for a second. So again, it's been around for a long time, before games and even computers. It comes from economics and other places as well. And the core idea behind this is that every possible action or state within a given model can be described with a single uniform value. So some kind of value, right? So again, the value, and usually referred to as utility, again, some kind of other value. It describes this idea of the usefulness of a given action within a given context. For example, again, here's a great idea, a great way of thinking about this. You need to buy a new toy for your cat, so you go online and find the perfect one. One website has it on sale for $4.99, and another website sells the exact same thing for $2.99. Well, assuming delivery times are the same, because that can also add into the utility, the value, you're going to choose a toy that's $2.99 because it's got the highest utility, because you're left with more money at the end. I have a certain amount of money, and at the end I'm left with more money. Therefore, that particular course of action, from an economic perspective, has the highest utility, we can say, right? Okay, so that's kind of where it starts. But let's suppose we have, we want to get this online toy for the cat. So you go online, find the perfect one. You're left with more money, which is kind of what we're saying here. But what if it gets more difficult? As an example, when you compare the value of two things that aren't directly comparable. So, for instance, we can sit there and say, let's assume that the two websites have different delivery times. The toy for $4.99 will arrive at your house in 2 days, while the toy for $2.99 will arrive at your house in 5 days. And in this case, the choice maybe is not longer as simple as comparing two price values. And maybe we need to convert time and money, right? Because there's some kind of relationship between time and money, let's just say. So we could say that each day is worth $1. because you're going to lose $1 of utility every day, which means that the total cost of the $4.99 toy, if $4.99 takes 2 days, is $6.99, while the total cost of the $2.99 toy, and $2.99 takes 5 days, is $7.99. So therefore the $4.99 toy is the winner because it's going to come faster, even though it's more expensive. That could be another way of calculating utility. So more complexity in the calculation of utility. So one thing to note is that utility is not the same as value. So value is a measurable quantity, such as the prices, right? Utility measures what we desire, right? It's very similar to this idea of insistence, right? But it's more complex in some ways, because what happens is, from an insistence perspective, we talked about insistence and motivations, right? And higher insistence and so on. But we can add additional details to insistence to create this idea of utility, to calculate the overall value of an action, whatever that's going to be. And think about this. If I can take an action, whatever the action is, and assign a value to it, right, any action, then doesn't it make it easier for me to do a comparison? It's easier for me to do a comparison with numbers than for me to do a comparison with, if, then, that, as an example. If I do a comparison with conditions, right, that's a different comparison than a comparison than with numbers. Numbers is really fast, especially on a decision tree. I have a utility of 13. Here's the utility of 12. I'm going to go for the highest utility. It's going to be 13 as an example, not 12. Right? So I'm going to go on this part of my decision tree as opposed to this part. How did I get the utility? How do I calculate it? That's a whole other thing, right? And it's another step outside of the actual decision tree itself. But here we can have the decision tree have a series of utility measures as opposed to comparisons if, and, or not kind of stuff. Here's another example. You're a billionaire. You would probably choose a cat toy that's $4.99 because you might value time more than money. So the $2 you save is nothing, right? $2, you save $2. Great. On the other hand, if you're really poor, here's another way of thinking about it. You would likely choose the cheaper toy and wait the extra time because the $2 is really important to you, right? And time is not as important as money, right? Because maybe you're not going to make money over time as much as a billionaire. So even though the money has the exact same value, but the utility for different scenarios is variable depending on the context, right? That's the idea here. So one thing to note is whenever we calculate utility scores, we want to create a consistent approach to this. Otherwise, what ends up happening is inconsistencies could lead to weird behaviors for our AI. That's the bottom line from this thing. And the other thing is, if I can compare utility scores to each other from a scalar perspective, right? A lot of times what we can do is we can normalize these values. So for example, let's say I have a scale in terms of actions from 1 to 10, and another scale would be from 1 to 5, right? Then what I want to do is normalize these two values so they're comparable, right? 1 to 10 and 1 to 5, we would have values that are normalized between 0 and 1, where 0 is 0% and 1 is 100%, right? And the way that would work is if I had a value of 1 out of 5, that would be a 0.2, right? 20%, 1 out of 5. Whereas 1 to 10, that would be 2 out of, the same value would be like, let's say, 2 out of 10, right? Because 2 out of 10 or 1 out of 5 is the same. Instead of comparing these two things, we convert them into a number range between 0 and 1, and now we're comparing apples to apples. 0.2 is still 0.2 no matter how you look at it. Okay, so that's normalization. Normalization is something that we use in games because we want to have this beautiful number range. 0 to 1 is something that we want to use over and over again. And we're going to see this also in physics a lot when we do physics simulations next semester. Okay. The other thing is that we can combine normalized scores really easily. We can average them, and since they're on the same scale, we can kind of say what's the average utility of a certain set of actions that we would take. So any value range can work as long as we take the overall value. So again, if an AI agent scores an action with a value of 15, You should know immediately that that this means that in the context of the whole system, for instance, does the 15 mean 15 out of 25 or 15%, right? And this is what we talk about when we say consistent values. We want to convert this into a normalized value so we can understand what it means, right? So again, the key here is calculate the utility, sometimes also called the weight for every AI agent. And what we want is to calculate it consistently. One thing that we note is also that most game worlds are now, the more popular ones are non-deterministic. So calculating the exact utility is not always possible. And the reason for this is because we don't know what the outcome of a particular action might be exactly. We can calculate the average outcome, right? And again, this is some math involved, but that utility would be affected by, in realistic situations, from the average outcome, whatever it's going to be, that might happen, right? Because we don't know, because it's non-deterministic. We don't know what the exact outcome is going to be. So it's kind of hard to know what the preferable action is if you can't really determine the results performing that action because it's non-deterministic. Okay. And so we have some math. Please don't be afraid of the math, guys. I'm not trying to make you crazy here, but the idea is we have this idea of expected utility, right? Where D is the desire, and you can see that here is this sigma here, this large sigma. It means usually sum, as an example, right? From where I starts at 1 to n, and D is the desire, and P is the probability of that particular outcome to occur, right? So you can create almost a calculation of expected utility based on the probability that the AI will take that action. Okay, so what do I mean by that? So we talked about this before, right? If we make a system deterministic, so the AI will always do a specific action, right, as an example, then it's less realistic, right? Even when it comes to motivations, this idea of insistence and discontentment, okay, these ideas, yes, but what if the AI doesn't always do the best action, right, to solve his discontentment or her discontentment? They're going to have a higher probability to do that action to solve the discontentment problem, right? Why is that? Because people don't always do the exact right thing. Maxim, you said that, and the sum of all p will always be equal to 1. Absolutely, right? Probability theory, right? So think about that for a second, right? If you have this idea of, I have this probability, and the total probability sum up to 1, right? Probabilities all sum up to 1. If I add up all the different kinds of actions together, right? So I have a 20% chance, that I'm going to eat, even though my insistence is high. As an example, if my insistence is high, 30% chance that I'm going to eat. I'm going to go and eat, even if my insistence for eating is high. But 70% chance I'm going to ignore my eating, because that's the kind of character I'm creating, right? And so my discontentment might rise, right? Higher than normal for my particular character, right? This idea of expected utility. What's the right action for me to do based on the probability that I'm going to do a certain action, right? That is more real, I would say, visceral, right? Makes more sense for us to program it this way as opposed to make it deterministic, where it's always going to be, we're going to always get the same result. So again, this is applied to every possible action, and the action with the highest expected utility is the one that's chosen. Expected utility, right? As opposed to the actual utility. We can't calculate the actual utility every time, right? So one of the things we want to, the way we've calculated utility is, we have a set of expected outcomes, and then depending on the set of expected outcomes, we create this idea of expected utility, right? But one thing we want to do is when we want to calculate the initial utility for a decision factor, and then we can go with what the next action is going to be. Okay, so let's go to that next level. So here's what we can do is we can apply a linear curve to the utility value, right? So example would be this. Let's suppose we have, and this is, again, we can talk about math, but the idea here is that let's suppose that I want to calculate when an enemy is near, right? What is the utility, right? The closer the enemy is, I want to increase the probability that I'm going to attack, right? As opposed to 100% I'm going to attack, okay? Always going to attack. But it's the nearer the enemy is from a radius perspective that I'm going to, kind of attack. So what's the maximum value? The maximum value would be inverse in this case, an inverse relationship between the distance from my character to the enemy. Let's suppose that it was a linear example. This is a linear curve, right? Where am I now? Where's the enemy now? If the enemy's 100 meters away, and if he's at 0 meters, as an example, then that's the highest utility, right? Because I would subtract the difference between where I am from the maximum value, right? So as the enemy approaches me, then the X value becomes higher and higher, right? As an example. If the enemy goes further away, the X value goes lower and lower, right? So it's less, my utility becomes less and less, as an example, as the enemy goes farther away. This idea of creating a multiplier for utility, right? And the reason this would work in this inverse way is because we just stated what the goal is. The goal is, if the enemy's close, I'm going to attack. If the enemy's farther away, I'm not going to attack. A higher chance not attacking, right? And so that's the utility. What's the next action? For me to engage the enemy, let's say engaging the enemy would be much higher if they're closer than if they're farther away. Okay? So it's kind of a linear curve in terms of how it would work. So Heart of Thorns AI, they actually did this idea. This is a kind of fairly recent game. I would say over the 5 or so years. Still, Guild Wars 2 is still pretty active. I think there's still an active community with this game. They created this idea of an infinite access utility system that uses utility that basically creates, allows characters' actions to be based on a data-driven, kind of system. So it's all data-driven. Everything is with numbers, okay? Which it helps them because what it does is it simplifies decision-making in many ways for the AI, even though it's very complex. An AI, especially when they're, in this kind of game world, have many, kind of decisions that can be made. Other motivations, not just collecting resources, but also defending or attacking or joining another group of AI, or whatever it's going to be. There's so many possibilities for this. So it helps to have some kind of system. And these guys, the people who made Guild Wars 2 and Heart of Thorns, they use this infinite access utility system. And actually, there's a GDC talk. If you actually look up infinite access utility system on GDC, they go through a whole discussion on, on utility AI and how this works. I'll post the GDC talk later on today as well. And by the way, just as an aside, just because I don't want to keep talking nonstop here, I highly recommend, if you don't have if you haven't had a chance to do so already, to look at some of those GDC talks from previous game developer conferences, all the way back to 2005. There's some really amazing things that were done in the past, and we can learn a lot from some of the decisions that game studios made when it came to creating AI, design decisions, everything from creating special effects, lighting models, animations, kinematics, and so on. There's so many things that you can learn from these talks, and I think they're public, a lot of them. There's also a GDC vault that is kind of a paid for service, but there's a lot of talks that are free on YouTube. All right. So again, there's a selection of decisions, right, that AI, we're going to continue with this thing. Here, what they did was they created this idea of a decision score evaluator. Now, once I think about decision score evaluators, in my mind, I'm thinking machine learning, right? Because we talk about a DSE as well in machine learning, right? A DSE. So a decision score evaluator is something that they're going to use for each different agent, depending on the species of agent, species of character that they've created here in their utility AI system, right? they have something called a think cycle in this architecture example, right? Which each decision score evaluator for an agent is scored, and the best scoring option determines the action that the AI takes for that particular think cycle, right? Which is kind of interesting, right? Now remember that we don't want to make a think cycle based on frames. Okay, I don't want to sit there and say, okay, I'm going to wait, 5 frames as an example necessarily, and then I'm going to go and think again, right? It could be based on other decisions, so a variable time, right, as opposed to a number of frames. You could use frames, but what you want to think about it in terms, which is better, might be game time, right? So how much game time actually passes for the character might be different than real time. A good example of this is in Minecraft. Minecraft, your day-night cycle goes really, really quickly compared to real life, right? So we can think of a think cycle being kind of within the context of the game time, whatever the game time you've created is, right? How long it takes. Even if you're playing something like as older as Oblivion, right? I'm thinking Oblivion or Skyrim as an example from Bethesda Game Studios. If you wait a little bit longer, if you walk as an example, time ticks from a game time perspective. And then what ends up happening is there is this day-night cycle or weather cycle that takes effect, right? And it doesn't happen in real time. Sometimes it's closer to real time. It might take an hour to walk across the game world in a large open world system, right? But that hour in real time might be several hours in game time, right? Even if you were to teleport or you want to quickly move from one location to the other, right, through some kind of portal system. I want to kind of fast travel to a particular place. Then the game time would be affected. You sometimes would start at a specific location in the morning, but you're fast traveling quite far away, and the game calculates how long it's going to take you in game time for you to get there, and so that it's much fast tracked that way. So the think cycle will be inside. When we were to think about a think cycle, I always think about it in terms of game time, not necessarily in terms of frame time. Okay. So again, we want to score this decision score evaluator. It basically is what we're doing is we're taking this idea of considerations. Okay, so now there's another thing we're looking at. In their system, what they've looked at is they called it a consideration, which is really some kind of raw numeric input that's normalized from an interval of 0 to 1. And usually those square brackets tell us that interval, 0 to 1, right? So some kind of thing. And then what we want to do is we want to process it across some kind of response curve. The last response curve we just talked about was a linear curve, right? Where, the farther something is, then the less utility there is. The closer something is, the higher utility it is. That's a linear curve, right? It's directly proportional to the distance or directly proportional to some kind of number in order for you to have take a specific action. Okay, that's what we're talking about. Okay. Again, think about this consideration now. We're talking about this idea of consideration, all right? So again, like we talked about, the DSC or decision score evaluator has two considerations. In this case, the distance to the target and maybe the health of the target, right? So we have two considerations. Health can be simple, right? We want to abstract it away from hit points and describe the overall healthiness of the target from 0 to 1, right? As an example, health. Distance can be normalized, like we talked about before. Sometimes what the authors of the GDC talked about was this idea of bookends. So what happens, as an example, if the distance of 100 meters might be the maximum and 0 might be the minimum, that's the bookends, minimum and maximum. And anything beyond 100 meters we don't really care about, right? We're not going to keep on normalizing a value that's beyond 100 meters because we don't care about anything beyond 100 meters, right? We just normalize between 100 meters and 0. Those are the bookends. And we can create bookends for a lot of scenarios because what ends up happening is sometimes it'll bring our scores out of whack, right? When we're kind of creating these considerations, if you will. Okay. Again, guys, we're into the last weeks of AI. And we need to talk about more AI stuff, when it comes to game compared to just simple techniques, which is what we've talked about all up until now, right? And that's why these discussions, these lecture is getting more complex. So don't be afraid of it. It's just, we need to talk a little bit about math, if we're talking about AI, right? And if you're interested in pursuing a career in AI, game AI, and so on, it's going to be way more complex than this. This is just really scratching the surface. All right, so we take these raw numbers and we want to process them across these different response curves. And the response curves that we're going to use, right, when it comes to this, as an example, we may not use a linear response curve, right? We might remap these things according to, a exponential response curve or a logarithmic response curve. Why is that? Because maybe, it's not going to be a linear relationship. Maybe it's going to be the farther you are, it's not directly proportional, it's inversely proportional or something else, right? Or the response is going to be, it's going to take there's going to be a lot more granularity to the numbers between 0.95 and 0.96 as an example. And why? Because once we start normalizing and we want to try and make create a consideration score, what we create is this fine-grained control over this idea of relative importance for each consideration. So if I look at things like one consideration compared to another, right, as an example, which one would win out? Well, depending on which response curve each consideration is applied against, then we're going to have different normalized values between 0 and 1, which is going to create, change my character's actions. I guess what's going to happen. One thing that we can also know is that any consideration can disqualify an entire decision from being selected by making 0, by selecting, by simply becoming 0. So a good example of this is, let's suppose that my consideration, if I don't spot the character, my actions is to patrol, right? As soon as I spot the character, in terms of consideration, if I was going to talk about motivation to patrol, right, as an example, if I spot the character, what's my motivation to patrol? 0, right? I don't want to patrol anymore. So one consideration, which is going to affect the decision of my character to take different action, might completely disqualify a whole other sets of actions, based on the utility of that action, right? So if as an example, I'm saying, okay, well, that was weird. It was like it disconnected and reconnected with the internet. I guess I've got a bit of a flaky internet, guys. I'm so sorry. All right. So AI designers, we talked about this idea of creating code for AI, but there's also this idea of designing for AI, right? And designing for AI all comes down to, we want to map out what's the next action. So again, before I do any kind of coding, I want to think about this, and I want to start thinking about, well, how is my AI going to respond when it comes to this scenario most of the time from a probability perspective. So we create these response curves, and again, one consideration can completely invalidate the other. Okay. So one of the things they talked about in Heart of Thorns is this idea of moment-to-moment tactical positioning and maneuvering of NPCs. Okay, so how would they do this moment-to-moment stuff? Remember, you can't do it every frame. It's going to be something where there's going to be a bit of a delay in terms of game time, right? So, so the choices are going to really be based on how much impact each NPC is going to have on the battlefield, let's say, as an example, right? So here's an example. We can have this common consideration, which is evade dangerous areas, right? For the AI, I'm going to evade dangerous areas. If the AI character is too close to a danger zone, they're going to be, the idea behind them is to rapidly move away from the danger area, right? And sometimes they'll play a specific kind of dodge animation, momentarily avoiding some kind of incoming attacks. But they're going to definitely get out of that, kind of get out of the fight, if you will, right? So that is definitely the idea of evade dangerous areas, right? So here's some considerations for evade dangerous areas. One, prevent action from being chosen in the middle of another action, okay? because we're in the middle of a dodge action, I don't want to mess up with that action before I do something else. Oh, I spelled the repetitions wrong. Of course. Let me save that. We also want to detect nearby dangerous activities in locales. So if I'm going to evade dangerous areas, I want to make sure that I'm not going to go from one dangerous area to another. Okay. Stop choosing this decision after a certain number of repetitions. Why? Because if I keep repeating my evade dangerous areas, then it becomes predictable, right? So that might be a consideration for me, right? My health value of the autonomous character, right? The higher the score, the lower the need to evade dangerous areas. So that might be something. These are all different kinds of considerations to take into effect when it comes to making that decision. And of course, all these considerations will be scored, right? Okay, close into melee when invisible. So imagine if I have a character, again, this is going back with Heart of Thorns. I want to close into melee range when I'm invisible. So it's like evade dangerous areas, but as a decision score evaluator, it attempts to get the character into a more advantageous position on the battlefield, almost like getting advantage, right? However, one of the things that might be is less widely applicable because only some characters will be able to be invisible at all, right? For example, maybe magic using characters as opposed to warrior characters. So what are the considerations for this? Prevent the decision from activating on all immobilized or otherwise occupied characters. So let's say I can't go invisible, when I'm invisible, if I'm immobilized, I don't want to even think about this decision to go into melee combat when I'm immobilized or if I'm occupied with doing something else, right? The other thing is, am I still invisible? If I'm moving towards melee combat, did my invisibility lapse, right? Did it time out, as an example? And if it did, then definitely not. I don't want to go into melee combat if I stop being invisible at a certain point. So there's going to be something that I'm going to check as I'm approaching the condition to take an attack, as an example. Move close to the target if the autonomous character can reach the target before turning visible. So this is kind of a consideration. And then finally, is my health value too low to risk this action, right? If my health value is too low to risk this action, then this would be a consideration that could negate all these other things. Okay, so that's kind of another way of thinking in terms of creating a utility system. Now, a lot of these things that we just talked about, they seem more abstract, right? The abstract ideas like prevent decision from activating on immobilized or otherwise occupied characters. How do you translate that into code, right? You're going to say, well, if I'm immobilized, then my consideration when it comes to this particular set of actions, even though my motivation is high to get into an advantage position, maybe that's one of my goals. Thinking about goal-oriented behavior, right? My discontentment from being, as an example, in the middle of the field, if I'm an NPC that needs to attack the enemy, if it's low, if it's very high, if I'm not doing anything, my discontentment might be high. However, if I'm already in the middle of a decision or I'm immobilized, then don't even think about this as a consideration for action. This is how it works. So again, recap. What we talked about was this idea of utility, the utility theory. How does it work, right? It's based on, it's not a value, but rather what is the best course of action based on the context, right? As an example of a particular AI. Where are they in the state of the game? What is the internal state? What is the external state? What are the considerations involved that are going to influence, right, the utility, the overall utility, which we're going to score between a 0 and 1, right, across all different kinds of actions. All actions are going to be scored between 0 and 1. And we're going to take the action that has the highest utility based on the context that the character is in. So utility theory, guys, it's a great idea. How does this affect you guys from assignment number 4 perspective? Well, let's look at assignment number 4, and let's think about utility theory and goal-oriented behavior. Okay, just for a second, because it could affect how you code your assignment number 4. Why is this? Because in assignment number 4, I've asked you guys to, well, actually, Alex and I, when we created this assignment, we talked about, first of all, it's built on assignment number 3. We talked about this earlier, but I'm just revisiting because I know you've just finished assignment number 3. And remember that assignment number 4 needs a complete working version of assignment number 3. You cannot do assignment number 4 without it, right? So it's a mandatory prerequisite. Even if your assignment number 3 is not the best, but you have most of the base done, and you've taken care of all your mandatory requirements for assignment 3, then you're good to go for assignment 4. Please make sure this is the case. If not, please talk to me later today. Okay. So take a look at these AI actions now. These are finally where we're going to get to making decisions, right? Patrol, right? The enemy will patrol along a predetermined path of nodes around the map. Play the move animation and related sound effects. Okay, so what is the motivation here from a utility perspective? In the beginning, or think about this as a consideration, right? The goal of the character, the enemy, to move around the map is to find the player, right? I'm actively looking for the player. Where is the player, right? If I find the player, the consideration to patrol is gone. I don't care about thinking about control, or patrolling anymore. Patrolling is not going to be even a factor anymore. Once I've spotted the character, I always know that the character is in play in how we've coded things, how we have asked you to make things. All right. Next one, move to the player requires line of sight. So there's a dependency here. So in order for me to move to the player, I need to have line of sight to where the player physically is. I'm not going to move to the player based on internal knowledge, right? For example, the computer knows the X and Y coordinates of the player, so therefore I'm going to move towards the player. No. Your AI needs to be able to see, quote unquote, the player, have line of sight in order for them to move towards the player, all right? So again, from a utility perspective, do I have line of sight? Yes. Then moving to the player has a higher utility than patrolling. Patrolling, 0. Move to the player, highest utility you can have, as an example. Now this is based on a deterministic scenario, right? So one thing we talked about in the lecture was we don't always want to have deterministic scenarios. Here in our little game, it's okay to be deterministic because remember, we're learning about AI, right? So I don't expect you to have a probability for what the AI is going to do. Okay, I saw the player. What's my chance that I'm going to attack the player? No. It's going to be 100%. Okay, if you see the player, you're going to attack the player, right? That's how it's going to be. Why? Because if we go to the other way, then it can complicate your coding. All right, and we only have a few short weeks to get this done. Close combat attack requires line of sight. Close combat distance, and close combat distance. That means you have to be within range, right? You play the close combat attack animation and related sound effects. Okay, so when do I do this? From a consideration perspective, can I do a close combat attack if I don't have a line of sight and if I'm not within close combat distance? No. So this consideration would be 0 for this particular action, as an example, and the utility would be low, right? Based on the fact that I can't really do, or 0, if you will, I can't really do this action unless these two other dependencies are met. Okay. So I want you to think of it in terms of that. What is the highest utility based on these things, especially when it comes to conflicting action? Like, for example, wait behind cover, move behind cover. All right. Well, if my motivation is to attack the player, right, as an example, but I've taken damage, then maybe my, the utility of moving behind cover because I want to save my life the AI is higher when I've taken a hit, compared to when I have higher health. And it talks about that, the actions down here. So we're going to have a couple of loadouts, which is something that I want you guys to plan for this next assignment, right? Your base enemy, you're going to extend the base enemy class, right, from assignment 3. And when it says subclass means you're going to extend the base enemy class. You're going to make a child class of the base enemy's superclass, right? It's going to start in patrol action, And here are the conditions. If the player is in their detection radius, and look at these things here, and they do not have line of sight on the player, then you want to activate or execute the move to line of sight action. I want to see if I can find the nearest node with line of sight. Now this, unfortunately, for us, realistically, is internal knowledge, because how would you know which node has line of sight, right? You're going to move to somewhere where it has line of sight. But you've heard the player. So if the player is in your detection radius, you know the general direction of the player, right? And this is why we created this scenario. If the close combat enemy has line of sight, then perform move to player action, right? So this means that the utility of doing this particular action is very, very high, right? A very high number of, as opposed to something low. And you can basically create utilities for each of the actions in order for you to perform them. If the close combat enemy has line of sight and is within close combat distance, then perform the close combat attack, right? So it satisfies the requirements so that you can do a close combat attack. These two requirements, we just put them in there twice to make sure that you know that the enemy will not be able to do a close combat attack unless they have both these requirements met. Okay? So again, I want you to read this carefully when you do your when you're doing your assignment. Make sure when you're starting to think about things, I would break it down into a series of action methods. Here are my action methods. My action method is going to come along with animations. It's going to come along with sound effects. It's going to come along with, you know, it's going to actually change the value or the utility of certain actions. You can specify these in different ways, and it depends on the structure you're going to use, the technique that you're going to use to make these actions. And there's 3 techniques we've talked about over the last few weeks. One of them is decision trees. Then we talked about behavior trees, and finally last week you talked about state machines. So any one of those types of techniques you guys can choose, or a combination thereof. If you want to use a state machine that has a decision tree or some kind of behavior tree, you know, inside of it or whatever, totally fine. Whatever makes sense for you, right? Here's what I don't want to see: if then else, like hard-coded if then else statements. That is not going to suffice. Okay, so if you don't use one of those structures, a decision tree, a behavior tree, or a state machine, you're not going to get your marks when it comes to you're going to lose marks for how some of this stuff works. All right, we also asked for a destructible environment and enemy responding. We created scenarios for you to make the game a game at this point. All right, so there's some things we've asked you to do. But more or less, think about these two loadouts. We have 2 loadouts: a close combat enemy and a ranged combat enemy. And we saw that in Herman's game, the example that I showed you guys last week. Okay, between these 2 kinds of loadouts. And there's also a third one that he created, which is a close combat, an enemy that can do both. That's as good as the player, or that has is a tank, has higher health and that kind of stuff, or some kind of armor defense. You know, those kind of things that he created in addition to these, right? For extra value, extra points. And we didn't give these things as an option, and the reason for this is because we thought, especially this semester, that there's going to be so much to do in terms of you know, how all this is scored. Take a look at the rubric, please. And in terms of all the things we've asked you to do, programming each AI action. Think about each action as a method, right, or a function, right, is worth marks. Okay. Thinking about the 2 loadouts, each loadout is also scored in terms of its behavior. Does it do what it's supposed to do? Does the close combat enemy patrol properly? Does the ranged enemy wait behind cover, move behind cover when it's hit, and so on? Does it do all those kind of things like it says, right? So please take a look at these things, because the weighting for your assignment is largely based on these 3 things: AI actions and the 2 loadouts. Okay. Questions around assignment 4 or anything else we talked about today in terms of utility AI, goal-oriented behavior, and rule-based systems? We talked about those 3 things today. All right, guys, so it's 11:20. We're quite early in terms of our time. We finished my lecture's done. Remember that we have our first lab starts at 12. And what I want to do is, I'm hoping that you and your partner are there. I want to go over, if I can, some of the assignment submissions in lab today, what I want to try and do there, and also start setting up code and thinking about ways of solving some of these problems in assignment number 4 from a technique perspective. How would you approach these, how would you go to the next level for your assignment number 4, right, in terms of programming out your actions and making your decisions. Okay, so that's what I want to really talk about in lab. So if there's no other questions, one thing to note is, again, there's 2 labs, one at 12 to 2, and the other one is from 3 to 5. A lot of times I get quite a few people coming in from the 12 to 2 lab. That's totally fine, as an example. And the 3 to 5 lab is, I guess, gets a little bit less love. But what I definitely will do, if there's something to, and I'm not sure if I'm going to record our lab from 3 to 5 again. It depends on how much time I get to spend with people that attend, and what I want to cover. If I can cover some of the programming aspects of whether it's decision trees, start thinking about decision trees, start thinking about how to program state machines, or start thinking about how to program behavior trees. Where am I going to go from that? And how do we set up the structure for those things? We'll talk about that today in lab. Okay, otherwise, guys, thank you so much, and I'll see you guys for some of you in 40 minutes, and for some other people this afternoon at 3 o'clock. Okay, guys, thank you so much, and we'll talk soon. All right.